graph of f of x equals e to the x and its tangent line. So here A, the thing that we are sliding around on this one, is the x value at which these two are intersecting. So A is giving us where the tangent line and the e to the x line curve are intersecting. And so the question was, as you change A, look on the left to see the function value f of a and the slope of the tangent line, m equals f prime of a. And what do you notice about these two values? So as you're moving a around, what do we notice about those two things?
The derivative and the regular function stay the same, the numbers.
Yes, exactly. Yes. So as we slide this, no matter where our tangent line is, f of a and f prime of a are exactly the same. So that's saying that no matter where we are on this f of x equals e to the x function, our exponential function where our base is e, no matter where we are on that function, the value of the function f of a is equal to the slope at that point. So if we take any x value and plug it into the function, it will be exactly the same as the slope right at that point. So if a is a 1 in this case, e to the x would of course just be e, which is roughly 2.71, etc. And the slope also, so if we plug that same 1 into f prime, we still have e 2.71, etc. Same thing for any value of a. If we bring it up to 2, f of 2 is exactly the same as f prime of 2. So this is another reason why e is super special. E is the only number that this will work with, the only exponential that this will work with. If we change this base to something else, I'll just change it briefly to 2. Now these are not the same at all anymore. But as long as we have e here, the function value and the derivative are exactly the same. That's also what we're seeing here. So we can't get exactly on e when we're moving this b around. But if we're at about 2.7, we can see that the derivative and the original function are the same. And I wonder if I can actually plug in e here. I can, there we go. So now they are definitely exactly the same. This is the only function that this happens for. The derivative is the exact same as the original function. And it's not just any exponential either. It is specifically the natural exponential, e to the x.
What happens if e is as a power? Does it have the same kind of?
If e is the power on you mean if we had like e raised to the e?
Yeah, not like b raised to the e. So instead of x, have e.
So if we just had e up here, then that is now just a constant function because any number raised to a constant number is just a number.
Okay.
So we do need to have x in the exponent or else it's not an exponential function. But x can be anything. So x will be e at some point as it's going along here. And so all of these properties will still be true when x happens to be e as it's moving along.
Okay.
Same thing for back here. If we were able to, like if I put e in for a, I guess this would have been a better graph to start this with. Now we're sort of off the chart. But this now, if A is E, our f of A is e to the e, and the slope is still the exact same thing. So E is a really special number, not just because it comes from this awesome limit from that compound interest formula. It's also incredibly special because it has this property, and it's the only function that has this property, that it is its own derivative. So if f of x equals e to the x, then f prime of x also equals e to the x. No other function does this. It is really very special. And it also makes our lives easier when we're taking derivatives because we don't have to do anything when there's an e to the x. It's
So
just,
is E typically always paired with like banking type situations?
not necessarily, but a lot. So it does give us that continuous interest, continuously compounded interest, but it also comes up a lot in any kind of growth models. So anything that grows exponentially, which could be like for some period of time, like bacteria in a petri dish would grow exponentially. And so this might be a way to model it. There are other exponential models, but E is used for a lot of kinds of growth things as well. Population growth,
Okay.
things like that.
Sciencey type things. Okay.
Yes, yes. And it just sort of pops up in a lot of places in math because it's so special. So all of that was just to make this conclusion that f of x, if f of x is e to the x, then f prime of x is also e to the x. So nothing happens when we take the derivative. So let's look at a couple examples using this derivative and make sure that if you didn't turn in that in-class activity quiz yet, do that. So all of the derivative rules that we know still apply. So we're just building on our derivative rules here. Ooh. And we're going to keep building those derivative rules through chapter 3. So we have 3 terms to consider: 3e to the x, 4x squared, and minus 2.
Would it be 3xe for the first one?
Nope. What is the derivative of e to the x?
The same as f of x. So it's exactly the same.
It is exactly the same, yes.
Okay.
So we know from chapter 2 that if we have a number multiplied in front of something, it just stays there. So that 3 is not doing anything, and the e to the x is just itself.
So does the e carry out throughout the rest of the equation, or is it just specific to that specific problem?
It's just that term, just the term with the e in it.
Okay. So then the next one would be 8x.
Yes, exactly.
Okay.
Can you kind of further explain? I'm not getting the whole 3ex and why it still just equals 3ex instead of 3xe or 3ex.
So, okay, so let's
I'm just
back
tired.
up for just a moment. No, it's okay. And it's weird because it's so, the fact that it doesn't change makes it really strange to use. So I want to first remind us of what our power rule is, because our power rule really can't apply to the e to the x. So the power rule says that if we have x raised to the n, let me move that. If we have f of x equals x to the n, then f prime of x is nx to the n minus 1. So the power rule only applies when n is a fixed number. N has to be something like 2 in the above example, or 5, or it could be a half or something like this. But for the power rule, the x, our variable, is always the base of that thing. It's never in the exponent. The exponents rule, exponential rule, is, I'm going to call it G for now, just so it's not mixed up with that other F. Now our variable x is up in the exponent. So this is a different situation from our power rule. Now we have a constant number e on the base of our exponent, and x is up in the exponent. And in that case, the derivative is just itself.
And that's just because it's not going to be changing?
It's because,
like you were saying in the power rule, like how x is a variable or x is a base. I mean.
Yes, so for the power rule, our variable is the base, and so it's a different kind of function. So power rule works for things like polynomials, even though the powers could be fractions or negatives and things. It's only for things where we have our variable on the base and then a number up in the exponent.
So if we had another constant as a base instead of e, the rule would still apply?
We actually have a slightly different rule for that, which we are going to see today.
You may have already said this, but will e ever be an exponent, or no, it can't, right?
It can be. We won't see that.
In the case
it
we
be.
did, would we just then use the power rule, or does it completely change?
So if it were, here's an example. If we had a function, f of x equals x to the e, so if we look at our two rules that we know here, we have the power rule and the exponential rule. Which one of these rules would apply to this x to the e?
The power rule.
Yes, exactly, the power rule. And that's because the base is actually x. So then we would bring e down and multiply in front. And then we would subtract e from the exponent. And since e is irrational, we call it e for a reason. So we would just leave it as e to the -1 because there's no other way to express it.
Gotcha. That was okay. Thank you.
Yeah.
So you wouldn't just take the E off?
No, we wouldn't.
Okay.
Because
All
e
right.
-1 is still 1.718 something, something, something.
Oh.
So this is not something you'll probably see, but it's totally possible. And that is a power rule situation since that x is on the bottom. And e in this case is our n because it's just some number. So let's look at another one similar. So we have this f of x. So we have two terms again. So let's look at each term independently. The 4x cubed part, what will be the derivative of that?
12x squared.
12x squared.
Yes, exactly, 12x squared. So that's just our power rule. Then the next term, minus 6e to the x. So now that x is up there in the exponent, so this is not a power rule anymore. So what will we get for that derivative?
Same thing, minus 6ex.
Exactly. Minus 6e to the x. So these are more problems where there's really no work to show here. Our power rule is just itself, and then e to the x doesn't change. So we don't actually have to show any work here. There's just this one step. So we're going to come back to this e, or it's going to show up more today. But section 3.2 is about derivatives of exponential and logarithmic functions. So we're not going to be doing as much investigating for logarithms. And actually, I'm going to move this down for just a second so we can remember. So we did some review of logs in that chapter 1 review assignment and the very first week of class. Natural log of x is log base e. So e and natural log are, or e to the x and natural log of x are actually inverse functions of each other, which we don't need to know at this time. But so natural log is another really important thing because it has to do with e. E makes things important. So this is sort of the base of our logarithmic functions is the natural log. So if we are going to take the derivative of natural log, this is it. And this is also in the book. Where did you go? Well, all of our exponential and logarithmic function rules are going to be on page 191, and we haven't gotten to all of them yet, but this rule is on 191. So if our function is the natural log of x, then f prime of x is 1 over x. So the natural exponential derivative of e to the x is e to the x, and derivative of natural log is 1 over x, are two things that you should know, and you can not focus on not memorizing them right now since you have a different test on Thursday, but those are two rules that you do need to know for the future test, the next test. So in the book, we are not going to go through this, but if you are interested in why this is true, the book goes through the 4-step process to find this derivative. And it's not something we're going to do in class because it's pretty involved, but it is a fact that if we take the limit as h goes to 0 of the natural log of x plus h minus the natural log of x over h, so that's the limit definition of derivative, that 4-step process, that limit does equal 1 over x. So that 1 over x didn't just come out of nowhere. It really does come from that limit definition of derivative. But people have done all of the work to find it. And so after your test on Thursday, you will not have to use this limit definition again. But it is in the book if you're interested to see how that process works for this, for the natural log. All you need to know, though, is that the derivative of natural log is 1 over x. So we're going to keep adding on these derivative rules. So here's our first example. I'm just going to write this up here so it's handy. So the derivative of natural log of x is 1 over x. And the derivative of e to the x is e to the x. So now we're finding y prime. So y equals 4x squared plus 2 ln x. So the 4x squared part is just our power rule. X is on the bottom, so we have 8x.
Is it just 1 over x?
Yes. So
Okay.
I'm going to rewrite this in a simplified way in a moment, but yes. So if we have a number multiplied in front of the thing, that's just still there. So the 2 is just hanging out there. And then we can focus on the derivative of natural log is 1 over x from our rule. It is more natural to write it. Oops. as 2 over x. So that 2 is just multiplying to be on top of the x. So it's just not quite
Is it-
simplified yet to write it as 2 times 1 over x. So I would say this is better.
Okay, and you want us to write it like the second one?
Yes.
Okay.
So we're just using this rule. If we see ln x and we're doing a derivative, that automatically changes to 1 over x. So let's do another one. So now we have natural log and e in the same problem. So let's do this first one in sort of in parts again. So that 1/3 is just there. It's just a number multiplied to what's coming next to it. So what is the derivative of natural log of x?
Just 1 over x.
Exactly, 1 over x. So then our next part, that 2 is just there still. So then we can look at e to the x. And what is the derivative of e to the x?
E to the x.
Yes, exactly. So we should, in the end, multiply that 1 over 3 times 1 over x to just get 1 over 3x.
Oh, I thought it was going to be 1/3 over x. I get it now, though.
Technically, it is the same, but this is the simplified version, so it looks better this way. So it can be a little weird to get used to these two new rules, our e to the x and our ln of x derivatives, but there's not a whole lot of action in the problems. It's just knowing if we're taking the derivative and we see ln of x, it changes to 1 over x, and knowing that e to the x is going to stay the same. So these are the two most important rules for exponentials and logs. E to the x is its own derivative. Derivative of ln of x is 1 over x. Before we build on that a little bit, are there any questions about these last couple examples? Okay. So this is all in your book. And let me make sure, yeah, it's all in here. So all of this is on page 191. I'll give you a minute to take that in. So it's a little blue box on page 191. There are basically 4 rules here, but really there's only 2 rules here. Exponential and logarithmic. So this is telling us that if we take the derivative of e to the x, it's just e to the x. So that is the first thing that we did today. And also the derivative of ln of x is 1 over x. So those are sort of our base cases in the exponential and log situations. But we, of course, can have exponentials that are of a different base, in which case we have this derivative. So if we're taking the derivative of b to the x, so b could be anything, then our derivative has that b to the x in it still, but then we have to multiply by the natural log of b. And if we're taking the derivative of any log, so log base b, we still have that 1 over x in it, but then we also have to multiply by 1 over ln b. So each of these still has that core part of, if we're doing the derivative of an exponential, the starting exponential will still be there. There's just a little more. And if we're doing the derivative of a log, we'll still have the 1 over x part, but there's a little more.
So are these like 4 different problems?
They are, well, they're all rules.
Oh, okay.
So these are all the rules for exponentials and logarithms. But technically, there's only 2 rules here because what is the natural log of e?
Natural log of e.
This is not a calculus question, no derivatives or anything, but if we evaluate the natural log of e, what do we get?
One over x.
So ignore the derivatives.
1.
Oh,
1.
sorry.
It's okay. I know we've been doing there's a lot going on above this.
Where's my brain going?
It's okay. So the natural log of e is just 1 because its natural log is the base e. So if we do the same base, a log of any base of that base is just 1. So really, if we look at the 2 rules on the right, if we put an e in here for b, this ln of b would just be 1. So we actually still have that e to the x rule there. And same thing for down here. If we let b be e, we would then have log base e, which is the natural log. And this whole part would go away because that would just be 1. So technically there's only 2 rules happening here. We just have the specific case for when we're working with e and the general case for any base. On the chapter 3 test, I will give you these 2 rules.
I have a quick question. How does b to the x become b to the x with the natural log of b? I'm not understanding where that natural log of b is coming in. Or is that just the rule and that's just the way it is?
That is just the rule.
Okay.
We can go through the process of where that comes from, but it is also in the book.
Okay. On 191.
The page, yes.
Okay.
Or 190-ish.
Okay.
So looking at this as this page is, it looks like a lot, but the natural log or the natural exponential and natural log are ones that you should know. So I will not give those 2 directly, the e and the natural log on the test, but I will give the general base b formulas on the test.
So I have a quick question. if there's a number in front of that natural log x, then the answer would be whatever that number is, and then 1 over x, and then you merge them together, basically.
Right, yes.
Okay. Will there ever be a power to that or an exponent?
Yes.
Okay,
And
we're getting there, sorry.
Yeah, we were getting there, but yes.
Okay.
There will be. And we have a couple ways to deal with it, but we'll see that in a minute.
Okay.
So I am going to rewrite those rules on the side here so that we have them on the same screen. So d dx of b to the x. What order did we write that in? Yeah. Okay, so we have this function g, x to the 10th plus 10 to the x. So one term at a time. What's the derivative of x to the 10th?
10x to the 9th.
10x to the 9th, exactly. That's our power rule.
Plus
How
10.
about 10 to the x?
Oh,
10.
So if it were 10x, it would be 10. But this
natural
is 10
log
raised to the x.
of 10. Is it natural log of 10 then?
That's a part of it.
Ten to the x natural log of 10.
Exactly. Yes.
Oh, wow. Okay.
So that is our exponential rule with any base. So in this case, b is 10 because we're taking 10 raised to the x power.
And that just is with any number to the x that we would do that?
Yes, exactly.
Okay.
So anytime we have a number and it's being raised to the x or whatever our variable is, that's our rule.
Okay.
So next one.
It would be 1 over natural log 2 times 1 over x.
Yes, exactly. So log base 2 of x is this log rule where b is now 2, our base. So that log base 2 of x turns into this whole 1 over ln 2 plus 1 over x times
And
1 over
that's-
x, excuse me.
Sorry,
Go
and
ahead.
that's the simplified version. Jeez, right?
We can do a little bit to make it look a little nicer, but I want to wait till the next step after we have the second log finished. But yes, that is basically simplified.
So is the next log 1 over 6 ln 5 times 1 over x?
So if we look at just the log part, log base 5 of x, that would be the 1 over ln 5 times 1 over x. But that 6 is just in front. So it's not actually a part of the log, it's just multiplying in front. So we would actually just be multiplying by 6 here. So the 6 isn't coming with the log, it's just kind of hanging out and multiplying with whatever comes after it.
So I'm sorry, just real quick, with that 6, you said it's just hanging out, right? And is that the case for everything? Like, say if we have like 100 log 7, the 100 would just be chilling?
Yes, exactly.
Got a chiller.
Yeah.
And I would prefer though, instead of writing it like this, where we have sort of each thing multiplied separately, that 6 should really just come on top because it's multiplying with fractions. So it would be like 6 over. My other recommendation is to bring that x in front of the ln. So x ln 2 minus 6 over x ln 5.
So does that negative sign does not distribute then?
There's nothing to distribute to because everything that comes after that negative is just being multiplied. So if we were adding and subtracting, it would, but. It's not totally necessary to write those x's out in front like I did, but if we're multiplying fractions, it's natural to multiply them together into one fraction. And the reason that I bring the x in front is that if we write ln 2 x, it looks like the x is a part of the natural log and it's really not. So that's why I like to put the x in front of the natural log.
I thought we were going to do 1x minus 1x and they would have canceled, but that was not the case.
No.
All right.
Yeah, since the x's are in the denominator, they'll just stay as they are. Most of the work for these problems is a matter of you finding the right rule and just sticking our numbers into the rule. So in this case, we had log base 2, so 2 was our b in the log rule. And then we had log base 5, so 5 was our b in the log rule.
Other than the instructions and the place we're at in the book, how would we know when to use this rule as far as like the 10x goes? 10 to the power of x.
We know because
that's the one that threw me a loop.
The x is in the exponent. That's the thing that tells us. So the place where x is tells us what rule to use. So since x is actually in the exponent, that is an exponential function. The 10 to the x, which means we use our exponential function rule.
So weird.
It is. Okay. So so we're going to do a word problem using this exponential stuff. So I'll give you a minute to read through this first. Okay, so we have an online store selling reversible fleece blankets, a very specific item, with a price demand function here. So in chapter 2, we saw price demand equations, in which case we always had linear equations. So now we have a price demand function where price is an exponential function of that demand x. So we want to find the rate of change of price. Anytime we see the phrase rate of change, we should automatically think derivative with respect to demand, when the demand is 400 blankets. So just as a reminder, P is the price and X is the demand. So this is the price that we can charge if we are selling X blankets. So rate of change of price when demand is 400 blankets. So first, in order to find rate of change, we need to know the derivative. So we're going to be finding, we could call it either P prime or dP dx. I just started writing dP dx, so we'll go with that. What kind of function is this? What does the x being in the exponent tell us? What kind of function has an x in the exponent?
Natural log.
Exponential?
Exponential, yes, exponential. Natural log will come into play when we're doing the derivative, but this is an exponential function. So that's the type of thing we should know. When we're doing a derivative, we should notice that x is up in the exponent, which means we're going to need to use one of our exponential rules, which I will just write over here again so it's handy. So our general exponential is that if we're doing the derivative of b to the x, our derivative is still b to the x, but then we have to multiply by natural log of x. Natural log of b, sorry. Ooh, natural log of b. What
So does that
is-
mean on this one again that 200 is just? Oh, I'm sorry.
No, go ahead.
I was just saying, is this one of those problems where the 200 is just kind of there on its
Yes,
own?
exactly.
So it'd be like 200 0.998xl.
Yes, yes, yes. So that 200 is just multiplying in front of the exponential part. So the exponential portion is just the part that is the base and the exponent, that 0.998 to the x. So what is our b in this case? What will be the b that we're plugging into our rule?
0.998.
Exactly, 0.998. So no matter what our base is, even if it's something weird like this, that's okay. That is just our base. So the 200 is just hanging out there. So we'll use this rule to fill in the rest of our derivative.
So do you put a bracket to separate that?
Yes,
Okay.
yeah, it's helpful.
0.998 to the x,
Exactly.
natural log 0.998.
Yes, exactly. So we're just taking that exponential derivative formula and identifying that b is 0.998 and then plugging that in for b. Which is not a very nice looking derivative, but that's okay. That's just how it works sometimes. So we have our derivative now, but the question specifically asked for find the rate of change of price with respect to demand when the demand is 400 blankets. So what are we going to do with that 400?
Substitute x with 400.
Exactly. So demand is 400. So we will do, now I'm wishing I had used prime notation, but we can use dp dx of 400. This is a function. So we're just going to plug in 400 for x. And that whole thing will just be evaluated in a calculator. So we have 200 times 0.998 to the 400 times natural log of 0.998.
Okay, so you multiply the natural log, the second
Yes.
portion? Okay.
Yes, exactly. And it didn't say how much to round to, but since we're talking about price, price is in dollars, so it would make sense to round to 2 decimal places. So I am getting negative 0.18.
Yep, negative 0.18.
So our last part of the question was to interpret the results. So what did all of that tell us?
There was a decrease of 18 cents per blanket that was over the 400.
Yes, so when we are making 400 blankets, the price is decreasing by 18 cents per blanket.
The production of 400, the revenue is decreasing at 0.18.
So we don't know about the decrease in revenue.
Oh, so this is not the same as the ones that we've been doing. Okay.
Right, but it's still the same idea of the rate of change of something, but we found the change in price per blanket, which
Okay.
definitely affects the revenue, but we don't know exactly what that effect would be. So I just put $0.18, but you could put 18 cents, and that would be fine. I just don't know how to type cents. So
I got a question.
Mhm.
So, is there a way you could find out how the price of the blankets would be increasing instead of decreasing?
So the rate of change would tell us when the price is increasing and decreasing. So specifically when it is 400, we're decreasing. But if we were able to find out when the derivative is positive, that would be where our price is increasing. So when the derivative is positive, we have an increase in price. Where the derivative is negative, we have a decrease in price. So we could technically take this derivative and set it greater than 0 and try to solve that.
Or you can put it into Desmos
Wouldn't
and just
be-
keep guessing numbers until you get
Yes, yeah,
to a
that's
positive mark.
I was gonna say that would be the more efficient way to do this. So if we did that, oops, what am I doing?
Will you scroll down just a little bit? Or are you changing screens?
Yes, I am, but you don't have to just yet. Go.
Okay, that's all I needed.
Okay. So if we were looking at a graph, our derivative function was 200.998 to the x ln 0.998. Why is that natural log looking so weird? Use this. So this window is going to need a lot of work. So our demand, we know, our demand is not, why is that happening? Demand is never going to be below 0. And our demand at this point went up to 400. So I'm just going to put 1,000 for now. Our price is probably not going to be changing a whole lot per blanket. So I'm just going to put like 10 and see what that looks like.
If you hit home, will it take you to it? Oh.
Home usually brings you back to 10, like 10 by 10 by 10.
Oh.
So I need to just make my y smaller. -1, 2, 1. There we go. So our price is increasing on this Oh wait, no, it's sorry, it's negative here. So this is our derivative function. So it's negative all the way here, and then it looks like it eventually becomes positive, or maybe not. Nope, it's still negative. Oh, there it is.
1, 0.
Nope, that's at 0. So there might be an asymptote here, actually. So this blanket might never increase in price. This wasn't a great graphing example, but this is our derivative function in this case. So it's showing us that the price is increasing continuously, but it's, or excuse me, the derivative is increasing continuously, but the rate of change of the price is negative this whole time.
So does that typically mean that they're never going to make any money on that blanket?
They might still be making a profit. The thing is, we don't know what the cost is.
Okay.
It just
Oh, sure.
means that the price is going down and down and down.
Mhm.
Which usually makes sense. As the demand goes up, price generally goes down.
I thought that as demand goes up, price goes up. If people want it, then they sell out, and then there's less for people to buy, and then price goes up.
You also got
That's
to
like
think about
supply
like
and demand.
droppage, spillage. The more stuff you make, the more mistakes you're going to be making too.
So as this is my price demand equation. If more, oh yes, you're right. I was thinking of price supply. I was mixing up my equations. You're right. As demand goes up, price goes up, and we can actually potential as the price or as the demand is going up, the price is also going up since it's an exponential function. I think this is just a bad example. I took this example from the book, but it's not giving a very good real world function, I don't think. It's a good example for finding the derivative of an exponential function, but it's not a great real world example of what might actually happen. So this is section 3.2. Next Tuesday, we will do section 3.3 and go on. And so we're going to keep building more and more ways to find derivatives of different kinds of functions. There is going to be a homework due next Tuesday on this, and it'll be a short homework since you have a test this week. It'll just be a little practice using the exponential and logarithmic rules. So
Thank
if there, if there are any questions, that we have a couple minutes left. Otherwise, I will see you on Thursday for a test day.
I was late showing up for class, and I was wondering, do we have to print out the test in order to take it, or can we just clearly write it on a sheet of paper?
You can write it on a separate sheet of paper. That's fine. Yeah.
Okay, cool, because I don't have a printer, so that works.
Yeah, I figured a lot of people probably don't, so you can just have it up on the screen and write on your paper.
Awesome, thank you.
You're welcome.
And
if
for
we usually use it, sorry, go ahead.
For Desmos, it's okay if we use the app on our phone as long as you can see our phone on our like computer screen workspace area, or does it need to be just on the computer? Because it's way easier for me to use it on my phone and I can just leave it in the computer area so you can see it on the screen.
Yeah, that
Or does it
would be,
need to be on my computer?
it's fine if you use it on your phone as long as it is in your work area and I can see that it's just Desmos and not other things.
Okay, cool. Sweet.
If we usually use a tablet Is that okay on the test as well? As long as it's in the camera?
Yes.
Okay.
Like to do your homework or do your
Yeah.
test. Yeah, that's fine.
Okay. All right, thank you.
Yes, you're welcome. And Jason, homework 4 is due tonight. Yes, 2.5 and 2.7. Wait. I don't know.